Dated back to as far as 3000 BC, the Egyptians developed a simpler technique of representing mixed fractions. This technique is known as Egyptian fractions.
The Egyptians used what we more commonly call unit fractions in the form of 1 over n. For example, a half and a quarter to depict any type of fraction, such as 2 over 5 or 3 quarters. In order for this to work, they wrote out fractions as a sum of unit fractions, where all said unit fractions are different. For example, 3 quarters equals a half plus a quarter. 6 over 7 equals a half plus a third plus 1 over 42.
This provides a much basic method of writing fractions, and especially useful when comparing them. However, most people want to know if every fraction can be represented in Egyptian fractions, and if so, how would this ever be helpful to us in the present day?
2000 years later, the famous mathematician Leonardo Fibonacci solved this and is now known as Fibonacci's greedy algorithm. As the name suggests, the idea is to take the largest unit fraction possible from the mixed fraction.
There is a lot of debate as to whether this works for every fraction.
Leonardo Fibonacci only used the greedy algorithm as a last resort in proving that all fractions can be represented in unit fractions. Now let's see how we can show this is true for all fractions x over y. We want x over y equals 1 over u1 plus 1 over u2 and extra plus 1 over un, where u1 is bigger than u2, etc., bigger than un, and you must take the largest u1 at each stage. Therefore, 1 over u1 is the largest such fraction.
This means that 1 over u1 is smaller than x over y. 1 over u1 is the largest unit fraction which is less than x over y. Then 1 over u1 minus 1 is greater than x over y. Since x is greater than 1, neither 1 over u1 nor 1 over u1 minus 1 is equal to x over y.
The remainder is x over y minus 1 over u1 is equal to x multiplied by u1 minus y over y multiplied by u1. Also, since 1 over u1 minus 1 is greater than x over y, then multiplying both sides by y, we have y over u1 minus 1 is greater than x. Or multiplying both sides by u1 minus 1 and expanding the brackets, then adding x and subtracting y to both sides, we have y is greater than x multiplied by u1 minus 1, y is greater than x1 multiplied by u1 minus x is greater than x multiplied by u1 minus y.
Now x times u1 minus y was the numerator of the remainder, and we have just shown that it is smaller than the original numerator x. If the remainder in its lowest terms has a 1 on the top, we have finished. Otherwise, we can repeat the process on the remainder, which has a smaller denominator, and so the remainder when we take off its largest unit fraction gets smaller still. Since x is a whole positive number, this process must inevitably terminate with a numerator of 1 at some stage.
That completes the proof that there is always a limited list of unit fractions whose sum is any given fraction x over y. We can find such a sum by taking the largest unit fraction at each stage and repeating on the remainder, hence the name, the greedy algorithm.
The most practical application of Egyptian fractions is in sharing or splitting.
I own a granary. I want to make 8 loaves of bread. But oh no, I only have 5 sacks of wheat. What on earth shall I do?
Oh, Michelle, what you need are Egyptian fractions.
Ooh, but I do not know of these Egyptian fractions that you speak of. They sound so ancient. I'm confused. Please help me.
Don't worry, I am here to help. First, you need to divide 5 by 8, and this is represented as half plus an eighth in Egyptian fractions. Therefore, you would split 4 of the 5 sacks in half, then split the remaining sack in eighths. Hence, there will be half a sack and eighth for each loaf of bread.
Many thanks, Akiki. You've saved me from a lot of problems. Bye. Another application of the Egyptian fractions was to measure field boundaries and to compare fractions. So many applications involved Egyptian fractions. And that's it from Sankavi, Yen and Rochelle. We hope you enjoyed our presentation and learnt a lot about Egyptian fractions. Bye!